Alright, so today I want to talk about voltage and current and resistance, and how those three things work, what they are, how they work with each other. So who knows what voltage, current, resistance are? Yeah? A few answers. Give me one of them.
What they are?
Yeah. Give me one of what?
Oh, one of the definitions?
Yeah.
Current, charge per time.
Charge per time. Good. Anyone else? Yeah?
Voltage is the potential difference.
Potential difference, right. And then resistance?
It's just resistance, no more resistance, harder than current.
That's good. Man, you guys are on top of this. So I can be brief with this. So for those of you who are just hearing about voltage, current, and resistance for the first time, it's really a question of how we characterize electron flow in this world. We can jump into quantum mechanics really quickly. And is everybody familiar about atoms, how they're made of a proton and a neutron and an electron? So that's in everything. So if I told you that electrons were everywhere, would you believe that? Yeah? Okay. Good. All right. So as long as we're on the same page there, we can move on. So if electrons are everywhere, then all we have to do is move them, right? That's all electrical engineering is either moving electrons or making electrons stay in one place. That's the whole game I play when I'm at work, is how to move electrons. Okay, so then what is the method that we use to move electrons? How could you motivate an electron to move? Yeah?
A voltage difference.
A voltage difference. So you can think of a voltage difference as our way of motivating electrons to get up and go. I'll make an analogy for you. If I said, all right, everybody sitting here, you guys look like you're comfortable sitting, working on your projects, great. Why don't you go run around the block? Just around the block. You know, sounds like fun, but probably nobody would do it. You'd probably want to stay and finish your projects or hang out or do whatever you want to do. Okay. What if I said $5 to anybody that runs around the block? Anybody interested? Who would go for $5? That's right. So I got a couple of you guys. All right. So that would be like a little voltage, a little bit of motivation. Now, what if I said $1,000 to anybody that makes around the block? You guys would all go, right? It's just around the block. Okay, so that's voltage. Depending on how much money I offer you, you're going to be more or less motivated to move. All right, now then there's another variable here to this analogy, and that is resistance. How can we represent resistance? So we already agreed that around the block is a track that I asked you to run. All right, what if I said run around the city? Whole city, all San Francisco. Who would run around the city for $5? No one? Robin probably would.
Always a guinea pig.
So nobody's going to do that. And the reason is because that track around the city is way harder than this track here. So it's going to take more motivation. If I offered you $1 million, would you do that?
Yeah.
Yeah, right? You'd walk, you'd run, you'd crawl, you'd do what it had to do to make it around the city. So it's, again, a question of motivation. So if an electron's sitting there, and I say, all right, go through this piece of metal. Electrons love going through metal. That's all they do. It's super easy for them to do it. It's like getting in their car and driving is metal. So they're like, sure, I'll go through metal, no problem. A volt, that's all I need, I'll do it. But then if I say, all right, I need you to go through this piece of plastic. I don't know about that. Seems pretty tough. I'm not going to go through. So the electrons decide I'm not going to go for 1 volt. Maybe for 10,000 volts, I'll make the jump and I'll make it happen for you. So bear in mind that it's all about the electrons, and feel free to personify them. I personify them often. They are people. They do what I ask them to do because I provide them the voltage to make it happen. So that's the two things that are voltage and resistance. There's a third one, and that's current. And you already said it, it's charge per time. So an electron represents a little bit of charge, a very small amount of charge. And so the number of electrons I get to flow through any given path is current. So like if I say, all right, I'm going to give you 1 volt to go and run through this wire and light up this LED. Give me an example. We'll do 1.5 because that's a AA battery. right? AA battery, 1.5 volts. Everybody agrees? Okay. So I'm going to say, all right, I want you to go with the 1.5 volts. I want you to go through this mini light bulb, right? This is a light bulb. So I want you to go through this mini light bulb for 1.5 volts. Yeah, I do that. No problem. And I say, all right, how many of you guys went through? So what I can do is I can make a cut here, and I can put, this is a, we'll call this a current meter. We'll also refer to this as a DMM, which stands for digital multimeter, which we have, there's one right there. So you can make a cut, and you put it through here, right? Just like that. And so you can use this current meter. What it does is it sits there and counts the electrons going through. So if I give a 1.5 volt signal here from a battery, and let's just say that this is 1,000 ohms. There's got to be a relationship, right, between voltage, current, and resistance. There's got to be. So I'll tell you, unless anybody knows how to relate voltage, current, resistance.
I equals V over R.
I equals V over R, otherwise known as V equals IR. And that is Ohm's law. So you know how people talk about 1,000 ohms? Ohms is a guy. He's the one that he's the one that discovered this relationship. So V equals IR, or V over R equals I, or however you want to arrange these three variables. So if we say that, and I've got 1.5 volts and 1,000 ohms, how much current am I going to have? Right, so it's going to be 1.5 volts equals I times 1,000, right? And this is ohms. So how many is that? What is that?
1,500.
I equals what?
1,500.
1,500. 1,500 times 1,000 is 1.5. We're way off.
It's like 0.0015.
Right. So you take 1, 2, 3 spots over. 1, 2, 3. So it'd be 1, 2, 3. Right. So it'd be 0.0. 1, 2, 3. Yeah. So it'd be 0.0015 amps. Right. Or 1.5 milliamps. That's what that would be. You guys all know this? It's pretty simple. Let me tell you something. This seems simple. This is like half of the electrical engineering discipline. Half of it. If you know this, you're halfway there. Don't tell the colleges. I'm telling you this. But seriously, most of what you would do as an electrical engineer is figure out different versions of this. And it gets more complicated, but most things boil down to that. Okay, so if you have current, you have voltage, and you have resistance. What if I told you today, right now, the current, if I take a AA battery, if I take this guy right here, I can use this 1.5 volts to put current through anything. Would you believe me? What if I said I could put current through you with this 1.5 volt battery? Would you believe it? You believe it? Does anybody not believe it? No? Is there anything that current won't flow through?
Things that don't conduct electricity.
But that's, what do you mean by don't conduct?
Doesn't go through.
Doesn't let current through, which would be another word for,
Insulator.
right, which is measured in ohms, right? So, really, it's not a question of conducting or not conducting, it's a question of how much it conducts. How much resistance is it? So I'll suggest to you that everything, I can make electricity flow through everything. Do you think electricity is flowing through me right now? Maybe? Just, that's exactly the right answer. Just a little bit. So if I told you that I have this AA battery here, and a person, and I went, all right, hold on to this. I'm just going to electrocute you, but only a little bit, right? That's what I can tell him. And I say this is again 1.5 volts. And let's say this guy is 1.5 mega ohms. 1,500,000 ohms. That's about right. Who's got a calculator? Who can tell me what the current is that's going to flow? So it's 1.5 volts, right? What goes here?
Oh, 1 million
Yeah, 1.5 times 10 to the 6th. And then what goes next? Current, I. Do we want to figure out? Right? So yes, there is current flowing. How much?
1 million.
One times 10 to the negative
1 times 10 to the negative 6 amps. That's 1 microamp. That's how much that is. So yes, right now there is current flowing through me. But obviously it doesn't bother me, does it? What if I stuck my fingers into an outlet? How do you think I'd feel?
Pretty shocked.
Pretty shocked. Clever. Right. So you'd be talking about much more current. So let's figure that out. How much voltage is in an outlet?
120.
120. That's RMS. Yeah, 120. We'll say 120. So if I take this guy and I say, all right. So now that you're not afraid of being electrocuted because you obviously don't conduct electricity, why don't you hold right? That's an outlet. Why don't you hold on to this? Go ahead, right? You don't conduct electricity. It's no big deal. Well, 120 equals 1.5 times 10 to the 6th times current. How much current do we have? Come on, calculator. I'm not going to do this math. It's a bad idea to do math on a board. That's why teachers make you do it. Because you really have to know it if you're going to put it on a board in front of you.
8 times 10 to the negative 10.
So that's like 80 microamps. That doesn't seem like a big difference, right? 1 microamp, 80 microamps. It's only 80 times as much, right? I mean, that's not a ton. I mean, okay, so let me take this battery. All right, I'm going to make you feel 80 times worse than this. All right, I don't care. I mean, I feel 0 bad right now, so 80 times 0 is 0, right? But it turns out that's enough to really have some bite and to make you kind of jump. So yeah, this is bad. 80 microamps is bad. How do you think somebody would feel with like 1,000 microamps or 1 million? Real bad. Put that through somebody's heart and it can stop. So it's all a question of, well, first people have different resistances. I'll have different from you. Even day to day, you'll have different resistances. And then also, how much power are you putting through yourself? So that's voltage, current, and resistance. Any questions? Does that all make sense? Should you guys be able to apply this all to your project? So if I sit there and I say, well, you're giving it an amp, or if you're giving it a volt, and you're putting it through a 10K resistor, you should be able to answer that question. Feel confident in being able to do that? Cool. That's everything I want to talk to you about today. Easy peasy. I'm impressed you guys knew so much. Well done.